Now, let's consider the idea of torque again. I introduced the idea of torque before as R times F. And I also showed that because F equals MA and A equals R times alpha, then the torque is going to be M R squared alpha, or in other words, I alpha. Now, let's go back to this definition of torque. How does this work? So we've got a mass out here, some distance r away, and I exert a force on it, and I'm trying to accelerate it. So we know that F equals ma, okay, and so that means this is m times r alpha. Now, again, we multiply both sides by r. That gives us my I alpha back again. Okay, so torque R times F. And so I turns out to be real useful, because that means that I could, for example, have a lawnmower blade or something, and I push on it, and now I find the eye of the lawnmower blade, and then that means that if I have this force, okay, and I want to know how fast does it rotate by exerting a force on it, then R times F equals I alpha. So then I can figure this out. And so that turns out to be this really useful sort of thing. But the interesting thing is that, again, you have something here, and so like a wrench, try to turn a bolt. And so you exert a force on it here, and that's going to exert a torque to try to turn the bolt. If you exert the force in the other direction, it exerts a torque in the other direction. So we can have a clockwise or a counterclockwise torque. But what this is telling you is, if you pull at a greater distance here, you're going to have a bigger torque. In other words, if the bigger the R is, the bigger the torque is going to be. Okay. So now we have this idea that the torque is related to the R. So if I try to pull the wrench really close up here, I don't have nearly as big an effect as if I pull it farther away. Now, there's actually this is actually considered in the manufacturing of wrenches. You notice that one problem you sometimes have is that if the bolt is on really tight, or a nut, and it can't get it off, that no matter how hard you pull, you can't get it off. And so some people have been known to slip a piece of pipe over the end of a wrench and pull on the end of it. That extends this R right here and gives them more torque. Now, the problem is that sometimes shears off the bolt, okay, because now you can break the bolt. And so that's not a good solution, unless you really know what you're doing and know how strong this thing is. You can either break the bolt or strip the threads, or in other ways damage the thing you're trying to do. And that's why when they manufacture wrenches, they know the average strength of the size nut or bolt that's used for. And so the smaller nuts, the smaller wrenches are not as big as the wrenches for bigger things. And that's actually done on purpose, because they understand the mechanics of how this works. Well, the other thing about this, so we know if we pull one way, we have a torque that is clockwise. On the other hand, if we pull the other way, there's a torque that's counterclockwise. So the torque has direction. What if I pull straight this way? Well, the wrench comes off. There's no torque at all. What if I pull this way? Well, it pushes onto here, but that doesn't do anything either. It doesn't make it turn. So what if I pull at an angle like that? Well, F has two components. It has one component this way and one component that way. So only the y component, the perpendicular component, matters. And so that is going to be equal to F sine theta, where that's theta right there. So the torque will be R times F times sine theta. And so that gives us the actual torque right there. Now I'm going to get back to that later because this RF sine theta comes back to us when we're talking about torques and when we're talking about the vectors of torque. So that'll be the next topic there with torque. But now we have a measure here, and then so the other thing here is so I pull like that. It's almost as if I've been pulling at a shorter distance. So if the wrench had been this way and I was pulling right there, that would have had the same torque as pulling from a bigger R at an angle. So if you imagine the perpendicular here, this D right here is R sine theta. That is called the moment arm. So that is going to be the effective distance in which you're pulling if you're pulling at an angle. And so occasionally I see somebody trying to turn something and twist something or whatever, and they pull at an angle like that, and that's actually less effective than if you pull perpendicular. Because you're effectively shortening the moment arm, and therefore you are reducing the torque. The torque equals RF sine theta, so you want sine theta to be a maximum. That means theta is going to be 90 degrees. And so this is our introduction now to torque.